very much. Sorry about the title. First, speak here. So in fact, at first, mention at the outset that this is. Does it work now?
Yeah, thank you.
Yes, so let me mention that this is partly joint work with Dave Cartieri of Max Planck Institute. And so my talk will be very foundational in nature. So I'll begin by asking perhaps a rhetorical question. So what is the difference between different types of geometry from the point of view of commutative algebra? Right. And of course, the answer is that the difference has to do with the type of functions that that we're allowed to use. Right. So if we think of geometry studying spaces with functions, this very much depends on what functions we can use to study our spaces. So, for instance, in algebraic geometry, so our spaces are locally modeled on algebras of this type. So, let's see, we just take some ground ring and look at a polynomial algebra, infinitely many variables in that ring, and maybe just mod out by some ideal. Well, whereas in differential geometry, the functions we have are smooth functions, infinity functions, and some are n, also maybe mod out by some ideal. So of course, all coordinate rings of manifolds are of this type, but of course there are more spaces which can be described in this way. And so the question is, well, what kind of structure we have on these algebras? So, well, here, of course, these are finitely generated commutative algebras over K. And here, well, these are also algebras over, in this case, R, the real numbers. Commutative are algebras, but there is something not quite right with this point of view. Well, the first thing that's not quite right is, well, obviously this this algebra is not finitely generated. As in our algebra, and yet, so when differential geometers do coordinate calculations, they always treat the coordinates here as if they were the local generators, right? So coordinates are treated as the generators. So in fact, with a good reason. So this is in fact well justified. So another thing that's not quite right with thinking of these algebras as merely commutative R algebras is something to do with coproducts. So we know that, well, in algebraic geometry, of course, products, so tensor products of coordinate rings correspond to products of the corresponding spaces. But here it's not true because, of course, if you just take, let's say, C infinity functions on Rn and take their tensor product over R with another such algebra, you will not get you will not get functions on the product of these spaces, so n plus m. You get something much less than that. So, well, to address this issue, one has to notice that that these coordinate rings actually have more structure than merely commutative R algebra, and this is something that was realized quite a long time ago, in the 70s, by Bill Lavier. But since this is not yet part of mathematical mainstream, let me recall the definition. So, first of all, there is an algebraic theory, or rather, say, the algebraic theory of C-infinity algebras. So is the category called C-infinity of Cartesian spaces, so the Rn's, and C-infinity maps between them. And now, what are C-infinity algebras? Well, they're algebras for this theory. So C-infinity algebra is a product-preserving functor from this category C-infinity to the category of sets. So, let's give it a name. Well, this functor is supposed to be product preserving, and in this category, every object is a product of, well, it's a finite power of a single one, namely the line R1. So such a functor is completely determined by its value on R1. So this is determined by set A, which is the value on R1, plus all the operations coming from the morphisms. So the operations and the operations, so AF from A to the power n to A. So there is one operation for each smooth function. And variables. Right, and of course these can be composed in an associative way, and so in particular, what we have here is an algebra over a certain operad in sets, operations given by these functions. But there is a bit more than that, having to do with the product structure here, which I will not dwell on. And so once we have this extra structure, yeah. So and we see, for example, that whereas this algebra was not finally generated as an R algebra, but it is finally generated as C-infinity algebra. So in particular, C-infinity of Rn is in fact free C-infinity algebra on n generators. coproduct. Let's denote it by this symbol, something other than the tensor product. So it's a coproduct on the category of C-infinity algebras. So by the way, the morphisms are of course just natural transformations of such functors. So this category such that now C-infinity of Rn coproduct with C-infinity of M, let's say, in fact is what you would expect. And this is true more generally for algebras, smooth functions and manifolds, for instance.
Product.
This is a coproduct. Coproduct. So this corresponds to product. This is a contravariant functor. So let's denote this by this free algebra and generators, while R adjoin three variables x1 through xn, but now I'm using the curly brackets instead of the square ones to distinguish these from polynomials.
So can you be a little bit more explicit about how you see C-infinity Rn as a C-infinity algebra?
I can do this for any manifold. For instance, if you have C-infinity functions on the manifold, they can be composed with smooth functions on Rn. So a function on a smooth function on the manifold is a function from n to R.
Yeah.
So if you have several such, then you should explain. So if you have, let's say, A equals C-infinity of some manifold, right? So you have
kind of convolution product then, right? You use diagonal on M and then...
That's right. So you say that. So if you have n such functions, one n, so this goes to Rn, and then you have any function from Rn to R. Say phi you can compose, and you get a new function from n to R. Yeah. Now, another thing to observe is that so inside this category C-infinity, there sits another, there's a smaller subcategory, which I call R. So this is a category with the same objects, so again, Cartesian spaces, but now you're only allowing polynomial maps. Polynomials only. And so product preserving functor from this into sets is the same thing as a commutative algebra. So I mean, any polynomial, of course, is a sum of products of the variables. So let's denote this included by J. And so from general theory of algebraic theories, every such map of theories leads to an injunction between the categories of algebras. So if you have these infinity algebras, category of commutative algebras, so there is the forgetful functor. So precomposition with J, which is forgetting part of the structure, and this has a left adjoint, which given commutative R algebra will freely generate a C-infinity algebra for you. So of course, get a feel of what this is. Well, the left adjoint must preserve free algebras. So if you start with the polynomial algebra and generators, you'll get the algebra of all smooth functions and those generators. But this free algebra functor can be deadly to some algebras. So, for example, if you look at this algebra, so polynomial algebra in one variable, so we're divided by this ideal. So, of course, this is the complex numbers. Now, if you apply G over 3 to it, so you will get the algebra of smooth functions in one variable divided by the same ideal. But now this function x squared plus 1 is invertible in this algebra. It wasn't in that one, but it is in this one. And so this is in fact the terminal algebra 0. Kind of thing that can happen. So now, what about derived geometry? So in going from the usual, the ordinary geometry to derived geometry, well, what's involved in the level of primitive algebra is topologizing.
So before you derive everything, so it somehow looks that it is related with localization. So can you take somehow like middle step taking power series? Because it's just localization what kills with 0. Because smooth functions are basically local. And so.
Right. Well, the power series, formal power series, also happen to have C infinity algebra structure. Well, basically because the smooth functions have Taylor series. Right. So this is here. You can do it in that way. So in fact, that's actually a nice point that the algebra of formal power series is also finitely generated C infinity algebra by Harel's theorem. So there is a surjective map from functions to their Taylor series. Yeah. Any more questions at this point? So now I'll try to derive everything. So what's involved is basically endowing your community algebras with a homotopy type. So for differential geometry, this would be C infinity algebras, let's say up to homotopy, or with the homotopy notion. By now there have been several ways proposed of modeling these. For example, so the first such proposal is due to David Spivak. So whereas the C infinity algebra was a functor from C infinity to the category C infinity into sets, we just replace sets with simplicial sets, and we look at functors like that. But now we have a homotopy theory here, so we look at functors which are only weakly product preserving. So the reason one might want to look at this way of modeling these homotopy C infinity rings is because, you don't have to do a whole lot to get a model structure on this category, because there are already model structures on diagram categories. Right? So functors from any category to a small category to simplicial sets. And so we can use one. We choose one of those. Let's say the injective one, and then we have these maps which we want to turn into weak equivalences. So we just localize those maps. We just take a Lebowski localization. Right. So that's all you have to say here. But of course, the trade-off here is the price you have to pay is these are quite complicated objects. Right? If you think about it, infinity algebras, which are already quite complicated, but then now you you make everything hold only up to homotopy. So that's quite complicated. So alternatively, you can just look at such functors which are strictly product preserving, right? Which is the same thing as turning things around. Just look at functors from delta op to C infinity algebras. Right, so it's just and this category also has a model structure which are much older than that, which is due to Quillen, and there is a result of Bediok, which says that these are in fact equivalent. Okay. Now, so when I started reading Spivak's paper, so what struck me is that, well, I thought that a lot of what's in there seemed needlessly complicated to me. So I thought, can we simplify this? So what I knew about is differential graded algebras, differential graded manifolds. So I asked myself, why not use DG manifolds to model these derived manifolds? So after all, these are basically like manifolds. They're manifestly smooth in the appropriate sense. So I think, as John Bias once put it, that these are just manifolds with bells and whistles. Right. And well, there is a good local theory for these. So there are minimal models, for instance. So which is kind of like Morse lemma. So this leads to, implies a sort of inverse function theorem. Oh. And so on. So cotangent complexes are very easily calculated in this setting. So let me maybe give an example. See what's going on. So, so in Spivak, for instance, he devotes quite a bit of time to computing the derived zero loci of functions. So let's say you've got some smooth map from Rn to Rm, and you want to compute its derived zero set. So let me just do it like this. And so he proves that these exist. They exist in general principles in his theory, but he never actually writes down what they are explicitly. And so, I mean, if you look at it, so what immediately struck me is that even before you had any kind of good homotopy theory on DG algebras, infinity DG algebras, whatever they turn out to be, if you make reasonable assumptions about the resulting homotopy theory is you can compute very easily what this thing is. So now on the level of coordinate rings, of course, this has to correspond to the following. So you just take C infinity of R M, C infinity of R N. So this is just pull back. And here we have the relation at 0. So what you end up computing is the derived coproduct. These guys, you just take C infinity of Rn. Rm. And so, if, well, like I said, if you make any reasonable assumptions about your homotopy theory, just basically saying that all these guys are cofibrant, then it turns out that you can represent this as what I call Ks, so which is, as an algebra, is just to take C infinity of Rn and then tensor it with the exterior algebra on M generators. So let me write it explicitly as x1 to xn and psi1 to psi m. So as a differential graded algebra, first of all, you just say that, well, degree of the psi is -1, and your differential is just this one. So it's the one that takes every xi to the corresponding function si. And this is something very classical. This is, in fact, the Kazoo complex. Okay. And so there's something that you'd see immediately, just by looking at it. So if you have a good theory, homotopy theory of C infinity DG algebras, whatever they are, then this would be the answer here. So this would be a local model for derived zero set of a smooth map. Now, of course, the problem is to make this rigorous. So if you look at this algebra, well, it certainly has C infinity structure. So this, in fact, is Ks. Is a C infinity superalgebra. And it is graded. But in general, you will run into contradictions if you just naively think of what this might be. So in general, being graded, in the naive sense, I must say, is incompatible with being C infinity for the following reason. So that's, there will be a problem as soon as you have, as soon as your algebra has homogeneous elements, say, of a degree other than 0, which are not nilpotent, which doesn't occur in that algebra, but in general it will. So if you just say, so you have in your algebra some element A, let's say of degree 2, then if it's C infinity, then you can apply a smooth function to it, and that will have to be in that algebra. So let's say take the exponential function. So it also must be in your algebra, but then this is not. So unless A is nilpotent, this is not a finite sum homogeneous components. So I guess you have to have another way of, a different way of understanding what a grading is. And so let me now say that, well, we basically succeeded in doing this and in building a good homotopy theory. And let me summarize the results. Going any further. Well, first of all, there is in fact a notion of a differential graded structure. On a C infinity superalgebra. Algebra. So defined in terms of an action of a certain monoid valued functor. Which we call E hat. So this is of endomorphisms of the odd line R0, 1. So have a theorem. Well, let's say theorem A. So there is a cofibrantly generated an almost right simplicial model structure on the category of, let's see, C infinity superalgebras endowed with an action of this monoid. With cohomology isomorphisms as the weak equivalences. And surjections in negative degrees. As the fibrations. So this is just like you have for differential graded commutative algebras over any ground wave containing the rationals. So that extends here as well. And another theorem that's the Dold-Kan part. So there is junction between the simplicial and differential graded superalgebras. Let's see. Let me denote this functor by curly n, and it's left adjoined by curly I. Which is equivalent equivalence. With respect to so our structure on the right and equivalence on the left. And yes, I should also mention, by the way, should have mentioned some time ago that there was a very nice paper by Borisov and Noel, which used simplicial infinity algebras of this model structure to greatly simplify what Spivak had done. And now what we show is that these approaches are in fact equivalent, ours and theirs. Let's see. So I should also say at this point that I'm greatly indebted to Pavel Scheverer for this insight of viewing differential graded structures in terms of an action of a certain monoid, a monoid object. This clarifies a great deal, at least for me. So it certainly sheds light on this correspondence, and in general, it allows one to treat simplicial, say, and differential graded structures on an equal footing. So in this approach, both kinds of structures become functors in some sense. So you can compare them directly. And so another thing I should also mention, so there is a remark. So the same approach, can be used in other contexts. So for example, for linear operads and algebras over them. So of course over a ring containing the rations. Before I go on to explain some of the details of all this, let me also discuss a few of the lessons we have learned while trying to prove these statements. One of the lessons is that in this whole business, so only this infinity structure on the degree 0 part. So the degree 0 part plays a substantial role. So I'll explain why in a few minutes. So for instance, on this side, so you have simplicial algebras, you have C-infinity algebras in every dimension, but actually it's only this extra structure, the C-infinity structure, only the one that's on the lowest dimension that plays a role. And this is somehow consistent, I think, with the view of all this derived information as being kind of an infinitesimal thickening of your scheme or C infinity scheme. So, then another lesson is, well, so what we actually did, we did something more general than this. So these results are valid not just for C infinity algebras, so that would be for differential geometry, but for many other types of commutative algebras. So you can ask yourself, if you have so any Labire theory containing the theory of commutative algebras, right? Maybe supercommutative algebras. So for which theories S does the same result hold? And the answer is so everything. So the above results hold for any S whose operations have derivatives, so-called Fermat property. And what's equally important, and the derivatives. So the Poincare lemma. So this is, in fact, the only thing that you need. So this is what works in every situation where this works, and also what fails where this fails. For instance, the failure of Poincare lemma. This is what you can ultimately trace the failure of homotopy theory of DG algebras over rings which do not contain the rationals. So this is exactly what goes wrong. So what I'm saying is that if it doesn't go wrong, so if you have antiderivative, so if every function has an antiderivative and any two differ by constant, that's really all you need for to be able to prove that theorem. Oh yes, so I must mention that what we haven't done. So I did say that we obtain a kind of simplicial structure in our model theory, but well, there is a different one on this side as well. What we have not done, we have not yet compared the simplicial structures on our model theories.
Is a simplicial structure a natural one on the right side?
There is a simplicial structure on this side, which is given by differential forms.
But the differential forms are graded in the wrong direction.
Yes,
So you
have to
can't-
truncate.
You can truncate and it's still an algebra. Is it?
Well, because it's you have to apply good truncation. So that's well,
Yeah.
what this Poincare lemma implies is that these differential forms are sacred. So you can take a coproduct with them and then truncate, and that's a safe thing to do. And well, I guess another thing I can mention here, now that you mentioned the kind of grading that you have here. So there are also results for non-negatively graded algebras. So with the right action, this monoid, and also for the unbounded ones. So you have the same answer there, except that you don't compare them with simplicial guys.
Are they bounded? Which they are bounded, these guys.
So what the so I'm using the convention that the differential should always increase the degrees. And so these algebras, so viewed as graded algebras, are non-negatively graded, so they're bounded above.
Non-positive.
Did I say? Yeah, non-positive. Thank you. They're non-positively graded, so they're bounded above. So the ones which are bounded below, so with the right action of this monoid should be compared with cosimplicial algebras, and there is a result also for those which I may get to if I have time, or then again I may not.
But I'm confused. When you say you're imposing a convention, you're not, because you're saying take R01 and take its endomorphisms. There's no convention. It just completely describes your theory.
Sure, it's just
So
that
when you say convention?
well, the convention is the
Logical
choice of
connection.
generators of the Lie algebra. There.
Okay.
Yeah,
Yeah,
let me just
okay.
I'll write it down again. So, okay, so let me first of all briefly mention that there is a theory of I was talking about T-infinity superalgebras without telling you what they are. So we have a theory as C infinity. So it's just like C infinity, except that now you use superspaces instead of Cartesian spaces. So this is the category of Cartesian superspaces. So R M n, so m greater than or equal to 0, and C infinity maps between them. Parity preserving, of course. And the C infinity superalgebra is by definition a C infinity algebra. So it's a functor, a product preserving functor from this category into sets. So you notice that this is in fact a two-sorted theory. So now operations are labeled by even and odd elements of C infinity of M, centered with the Grassmann algebra and then generators. So it's now a two-colored operad, but everything else is just as before. So again, you have the polynomials embedding here and corresponding adjunction level of algebras. Let's see. Now, very important thing to notice here is that these C infinity structures they extend uniquely to nilpotent extensions by the Taylor form. super or not, that's the case. So it extends to split the opposing extensions. So in particular, well, of course, these grasping algebras so they're automatically infinity algebras, and like with every nilpotent extension, so taking the co-product with such an algebra is the same as just taking the usual tensor product as I've been doing, and moreover, so this has a left join. So that's called co-exponentiality. So if you denote like this. Now the odd line you can think of as just this functor from commutative algebras to sets, which is co-represented by the graphing algebra on one generator. So this, of course, you can also into this C infinity. Let me just denote this by hat, R01 hat, even though it's really the same thing, it's just viewed as a functor from C infinity algebras. So they're both co-represented by lambda 1 in both cases. And because of this co-exponentiality, you can look at the functor E, which is R01 to R01. You can also extend along this projection functor. And this is what I call my E hat. And so these are also co-representable. So E is co-represented by so something that has an algebra. It's just R join one even and one odd variable. And so it's hat by J lower streak of this, which is the algebra of smooth functions from one even and one odd variable. Now, as monoids, these have the following structure. So we have E is isomorphic to the semi-direct product of the multiplicity monoid and the odd additive group and correspondingly we have the same, but now they're smooth versions. And of course, it's well known that an action of this monoid is exactly the same thing as a grading and a differential. So now the Lie algebra, in both cases the same one with small e, so the superspace is R11, and this is of course just the derivations of this guy. So it's generated by, you see, this derivation and this derivation. And so in response to Ezra's question, so this is in fact my convention. So I put the minus sign so that you have the differential increasing rather than decreasing in degrees. But that, of course, means that the gradient will be the opposite of the chain gradient. So, very little time. So, let me just now explain what.
But my point was simply that we're firmly placed in the simplicial setting by this choice.
Yes, well, otherwise.
There's no flexibility to go to the co-simplicial story
Right.
using this monoid.
But then, well, you see, this monoid is not commutative, so it matters from which side it acts.
Ah.
Just like, well, simplicial and co-simplicial are not the same thing.
Oh.
The same reason. Okay, so, this is where was it? So let me just say that so it's a given an action. So if you have an action, so that just means that if you have a coaction of this thing, from the algebra. So this is, it doesn't mean that A becomes a differential graded algebra for the reason that I said before, but it has a subalgebra which is. So like this, just well, the subalgebra corresponding to the algebraic part of this coaction system. So this is phi inverse A. So this is in fact a differential graded algebra. This is a DJ algebra. With a infinity structure, which remains on the degree 0 part, so the invariant part. In particular, every such algebra with an E-hat action has an underlying chain complex. So we can use that to induce the model structure. So let's see, we have infinity algebras hat. And have non-positive graded co-chain complexes of supervector spaces. And so here in the middle, we have what I could call non-negative and non-positively graded DG SC infinity algebras, which are just DG algebras with this additional SC infinity structure in the zero part. So we have the adjunctions here. So we induce the model structures here and here. And in fact, this is done in such a way. So this adjunction is in fact equivalent equivalence. So I should stop here. So I wanted to say, well, at least define those functors. But I'm out of time, so I'll stop.
Any questions or comments?
Can you say something about how the coproduct is defined on C-infinity algebras?
Well, it's this category of algebras over an algebraic theory. So it has, well, it's automatically completed co-complete. But so in more concrete terms,
Is it some sort of deconvolution, or is it?
no, it's the first thing you do is well, you can define it on free algebras, and that's obvious. But then you can choose. Well, so for any other algebra which is not free, you can choose a presentation, and that's a sort of co-limit, so that should be preserved. And a special feature of of this theory, or any theories that work in this context, so that satisfy the Fermat property. And one of the consequences of that is that an ordinary ring theoretic ideal in any such algebra defines a congruence consistent with that structure. So in the quotient, you get canonically the same, in this case, C-infinity structure. Right. So, so if you know, where did I write this? So if you know how to define the coproduct of A and B, then you know how to define the coproduct of these guys, say coproduct B divided by the sum of the two ideals, I and J, just like this. So it's, well, I guess in the same way as you do for ordinary algebras.
How complicated does the list of generating trivial cofibrations look?
It's the same as for algebras, the standard ones, except that they you have to take they're C-infinity algebras. So
SC infinity.
or S infinity.
Okay.
They're exactly the same.
I just wondered if, when you were talking about the example of the derived zero set, have you looked at the work that Joyce and Brav and those people have been doing on that?
Yes, I would mention if I had time. So right. So I also understand the relation with their work. So you can let's see, where was my Dold-Kan statement? So on both sides you can take truncations to get what you might call two algebras instead of infinity. So in this case, you would get the groupoidal C-infinity algebras. So it's just functors into groupoid special sets. And on this side, you just have DG algebras, which are concentrated in degrees 0 and -1. And so those two categories are actually not just Quillen equivalent, but equivalent. Right? This. Well, I have an explanation for this. It's a bit involved. It's just basically saying that the thing that goes wrong on the simplicial side, say if you have a DG algebra, just a DG algebra, so you want to try to force, so you apply the Dold-Kan functor to the underlying space and try to force an algebra on the result, and so what you will get is only an E-infinity algebra in general, not a strictly commutative algebra. But the problems only start at dimensions higher than 1, so to speak. So if you have anything above dimension 1, you'll get a strictly commutative algebra. So everything works just fine in that case.
Is there a way of understanding classical Dold-Kan correspondence via monoid action?
Yes, I guess I didn't tell you what those functors are. So you can do this for anything or any kind of objects on which these act. So they can act linearly on.
But what's the monoid in the classical? In the classical
It's where did I erase it? Yeah, well, it's this one. It's just the semi-direct. I mean, works out to the semi-direct product of the multiplied monoid, which gives you the grading, and the odd additive group, which gives you these odd translations, the differential, in other words.
Do you have some comments on the others, the other functors?
The other, so you mean
Yeah,
meaning
so the
co-simplicial instead of
action on the other
simplicial? Yes, so you can. So on the simplicial side, you have. Let's see, infinity algebras. Co-simplicial here, and you have. These guys. So we also have now. So the right adjoint goes from here to here, and it's actually the co-simplicial version of the Dold-Kan functor. Just like this one happens basically to be isomorphic to normalization. And its left adjoint is denoted by S check, because this is essentially it's essentially the functor that was constructed by Pavel Scherer in the opposite category of supermanifolds. So yes, you have also a simplicial statement like that.
And in this case, what is the model structure on the left side?
Well, it's well, on the simplicial side, as always, it's a bit artificial. So you just reduce it via the chain complexes.
But what's the model structure? There's the homotopy theory there on the left
Right.
side.
So a simplicial algebra has an underlying normalized co-chain complex.
So it's again quasi-isomorphic then.
Yes, it's the same one. Just like, well, without the C-infinities, it's the same thing. I'm not sure it's it's good for anything, such a model structure here, but it exists.
Just to postpone further questions to the private discussion and thank the speaker again.